In today's video, we're going to talk about absolute value, order of operations, and divisibility rules. So let's first take a look at what is the absolute value of a number. The definition of the absolute value is that the absolute value of a number is that only the magnitude of the number without regard for the sign. We usually use two vertical bar lines to represent that. So we can say the absolute value of x. Example would be the absolute value of -3, and we only take the magnitude of -3 with not the sign, so it's just 3. The absolute value of 5 is just the magnitude of 5, which is just 5. The absolute value of -3 minus 2 is just the absolute value of -5, and it's just the magnitude of -5, it's just 5. A better definition would be the absolute value of a number is essentially the distance this number is away from 0. So let's say we want to find what is the absolute value of -4. We first pinpoint the location of -4 on a number line, and we find what is the distance from -4 to 0. So we can clearly see that it's 1, 2, 3, 4 steps away from 0. So it is just 4. And as the distance of something is never negative, so the absolute value of a number is also non-negative. In another word, it is always greater than or equal to 0. In order of operation, absolute value serves as a bracket, so it has the same priority as a bracket. So next, we're going to take a look at the order of operation. A very useful acronym is BEDMAS. First, B stands for brackets, any types of bracket, a parenthesis, a square bracket, a curly braces, or the absolute value bracket. Next, E. E stands for exponent, so x to the power of y or something in this form. D and M have the same priority. D stands for division, and M stands for multiplication. They have the same priority. A and S also have the same priority, where A stands for addition and S stands for subtraction. So knowing the basic order of operation, let's take a look at a relatively challenging evaluation. So you want to evaluate the absolute value of 4 minus 7 plus bracket -2 minus 4 over 3 cubed divided by 4 over 9. So the original expression is equal to. So you want to strictly follow BEDMAS, otherwise our answer would be wrong. So you want to solve for bracket first. We want to evaluate anything that's inside the bracket. So we can clearly see that we have two brackets here. So we want to evaluate those two first. So the absolute value of 4 minus 7 is the absolute value of -3 plus bracket -2 minus 4 over 3 is -10 over 3 cubed minus 4 over 9. However, we have not yet fully evaluated this absolute value because the bracket is still here. So the absolute value for -3 is only the magnitude of -3 is 3. Next, we want to solve for exponent. So we can see that we only have one exponent here. So we just calculate that. So -10 over 3 cubed is just -1000 over 27 divided by, and we just copy the divided by 4 over 9 down. Next, we do either division or multiplication. So we can see that we have a division here. And the way we do this kind of divided by a fraction is a method called keep, change, flip. It's fairly simple. So first we copy the first part down, and then we do the division. So keep, we just keep the dividend, the -1000 over 27, as it was. and we change the operation sign to its opposite. So the opposite of the divide is multiplication. And then we flip the fraction upside down. The original numerator becomes the new denominator, and the original denominator becomes the new numerator. And now we can just perform the multiplication, which is fairly simple. So 9 and 27 gives us a 3 right here. 4,000 is just 250. So it becomes negative 250 over 3. And now we can do addition or subtraction. So plus, minus, so we want to add a negative number that is just minus. So 3 minus 250 over 3. And we want to find the common denominator, so we convert 3 into a fraction, 9 over 3, minus 250 over 3, which gives us 241 over 3, negative 241 over 3. And this would be the final answer for this expression evaluation question. Next, we want to, let's take a look at divisibility rules. So first, what number can be is divisible by 2? It's just all even numbers. So anything like 2, 4, 6, 8, and so on. Divisible by 3 is just the sum of digits of this number. If the sum of digits of this number is divisible by 3, then the whole number is divisible by 3. Example would be 273. So first we want to find the sum of digits. So 2 plus 7 plus 3 gives us 12. And we can see that 3 divides 12. And this vertical bar line here means divide. So if we have something like x vertical bar line y, this means x divides y, or y is divisible by x. And mathematically, it just means y divided by x equal to some number k with remainder of 0. So, come back to the example. We already find that the sum of digits of 273, which is 12, it is divisible by 3. So, the original number, 273, is also divisible by 3. That's just the method we are using right here. Next, divisible by 4. We just check the last 2 digits, and if the last 2 digits of the number is divisible by 4, then the whole number is divisible by 4. Example, 781,916. We just check the last 2 digits, 16, and we see that 4 divides 16, because 16 divided by 4 equal to 4 with a remainder of 0. So we can say that the original number 781,916 is also divisible by 4. It's just we check the last 2 digits, and that's it. Divisible by 5 is any numbers that end in 0 or 5, and I think that's fairly simple. Divisible by 6 is any numbers that is divisible by both 2 and 3. So a number that is even and the sum of digits is divisible by 3 at the same time. So both conditions corresponding to 2 and 3, divisibility rules. Divisible by 7. This one's very interesting. So we perform primarily 2 steps. So we take the last digit of a number, we double it, and we subtract it from the remaining digits. And we can repeat this process over and over again to reduce the magnitude of the number that we are judging. So if the residue of this operation is divisible by 7, then the initial number is also divisible by 7. So one example would be 357. So first, we take the last digits, we double it, we get 14, because 7 times 2 is 14, and we subtract this 14 from the remaining digits, which is 35. So minus this, we got 21. And we can see that 21 equal to 3 times 7. So 7 divides 21. If this is true, because 7 divides 21, therefore 357, reverse order. Therefore, 357 is also divisible by 7. Another example would be right here, 6,965. So first, we want to double the last digit and subtract this 10 from the remaining digits. We got 686. And 686 is still fairly large. It is difficult to judge if it's divisible by 7. So we can take the last digit 6 again, we times 2. We got 12, and we subtracted that from the remaining digits. We get 46. And 46 is equal to 7 times 8. So 7 divides this 56. And because of this, we can say that the original number, 6965, is also divisible by 7. And this is just how the algebraic way we can use to judge if a number is divisible by 7 or not. Divisible by 8, we just check the last 3 digits. So recap, if we want to judge a number is divisible by 4 or not, we check the last 2 digits. And if we want to judge a number is divisible by 8 or not, we check the last 3 digits. So in this case, 54,600, we just check the last 3 digits, 600. Is 600 divisible by 8? And we can see that 600 divided by 8, we got a 75. That's right, with a remainder of 0. So we can say that because 8 divides 600, the last 3 digits, therefore the initial number 54,600 is also divisible by 8. Divisible by 9 is very similar to divisibility for rule for 3. So we just check the sum of digits, and if the sum of digits is divisible by 9, then the initial number, it is divisible by 9 as well. So examples right here. So we find the sum of digits first, 3 plus 7 plus 5 plus 3, we get 18. And because 18 is divisible by 9, therefore the original number 3753 is also divisible by 9. Next, divisible by 10 is just any number that ending 0. For example, 100, 150, 2,300, just the last digit, and it's 0, and it's fine. Next, divisible by 11. We use a method called O minus E, odd minus even. So let's take 5,291 as an example. So we want to start from the very right. So let's label the digit right here. So this, let's say it's the first digit, the second digit, the third digit, and the fourth digit. We want to first find the sum of all the numbers, all the digits that has a odd index, which is basically first and third. So the sum of all the digits that has an odd index is 1 plus 2 equal to 3. 1 plus 2. And then, similarly, we want to find the sum of all the digits that have an even index, which is 2 and 4. So corresponding to 5 and 9, we get 14. And then we want to perform this O minus E. So odd minus even, 14, we get negative 11. And we just need to simply check, is this negative 11 is the result of this O minus E divisible by 11? And we can say that, yes, it does, because negative 11 divided by 11 we get a -1 with a remainder of 0. So -11 is divisible by 11. So if the result of this O minus E operation is divisible by 11, then we can say that the original number 5291 is divisible by 11. So we just do this O minus E. We be careful that we label the digit from the very right end. Next, divisible by 12 is just any numbers that are divisible by both 3 and 4. So we recap. For 3, it's just sum of digits that is divisible by 3. And 4 is just last 2 digits. If they are divisible by 4, then the number is divisible by 4. Next, check prime number. So if we have a fairly large number and there is no very conspicuous sign of any divisibility rules, how can we decide if they are divisible by if they are prime number or not? So we can just check if the number is divisible by all whole numbers less than the nearest square root of the initial number. If the initial number is divisible by none of these whole numbers, then it is a prime number. Example, is 143 a prime number? So first, we want to find what is the nearest square root of this number. So we can see that the square root of 144 is 12, and the perfect square that's just less than 143 is 121, and it gives us 11. So you want to go with this 11 right here. You want to go with the nearest square root. So since 143 is nearer to the 144, so you want to go with this 12. So you want to just check if 143 is divisible by any number that is the whole number that is less than 12. So essentially from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If none of these numbers are divides 143, then 143 is a prime number. So 1, yes. 2, 143 is not an even number, so no. 3, 1 plus 4 plus 3 gives 8. 8 is not divisible by 3, so not 3. 4, last 2 digits, 43 is not divisible by 4. 5 only works when the last digit is 5 or 0, and the last digit in this case is 3, so no. 6, we need to satisfy both 2 and 3, and none of them is satisfied, so no. 7, we take this letter, take this number, take the last digit times 2, subtract this from the remaining digits, we got 8, and 8 is not divisible by 7, so no. 8 last 3 digits, and we can see that no. 9, we still use the sum of digits, so 1 plus 4 plus 3, we get an 8. 8 is not divisible by 9, so no. 10, only if the last digit ends in 0, so no. 11, we do O minus E, so 143. We label the digit from the very right end to 1, 2, 3, and we can see that odd is index 1 and index 3, so 1 plus 3 equal to 4, and even is just index 2, which is 4, and O minus E equal to 4 minus 4 equal to 0. And we can see that because 0, because 0 is divisible by 11. So this 143 is also divisible by 11. So actually 11 is a yes. And 12 we need to satisfy both 3 and 4, and none of them are satisfied right here, so no. So we can see that among the whole numbers that are less than the nearest square root, which is 12 of this initial number, one of them is actually the factor of 143. So 143 is actually not a prime number. That's how we decide. Thank you very much. I think that's all for today's video. Thank you for watching.